Yes.
I try to find the good.
We have
Yeah, okay. I think it's okay like that.
Okay, good, nice. Thank you. So I'll we'll just do welcome everyone. It's great to be here with you all and virtually, I guess. And I want to thank you all for joining us. And we're, starting our 2025 part of the Virtual Aeolian seminar series. Philippe and Maddie Kelly, who isn't here because she's in the US, so time zones wise, and Jean Brand are we're all part of the ISAR board, and we're excited to continue these Virtualian seminar series with Laurie Barrier. But before I turn it over to Philippe to introduce Laurie, this is the sort of structure we have. So please keep your microphone off unless called on in the question and answer section, which we'll have after her talk. And please just feel free to type questions in the chat at any time, and we'll get to them. But we'll wait until the end to read them out loud. During the Q&A, you can also raise your hand if you prefer to speak out loud. So we'll try and keep mics off unless we sort of host it together. And this meeting is being recorded. As you can see, you probably got a notification about that, and will be shared with the ISAR community afterwards. So if you want to, you can hang around with us until the end, and we have some, well, I guess this is the main update, and we have some more updates to share, I guess, afterwards. We'll ask everyone to contribute to creating and maintaining a welcoming and respectful working environment that fosters diversity, inclusion, and belonging. So now to Philippe.
Thank you. Welcome everyone, and welcome Laurie. Thank you for accepting to give this talk. So just a few words to introduce you. So Laurie, you did your PhD thesis in Rennes in France about interactions between tectonic and fluvial sedimentary processes in mountain ranges. And then you had another position in at the Institut Français du Pétrole in France, and then you moved again to your current position at the Institut Physique du Globe in Paris. And so you are a geologist specialized in sedimentology, geomorphology, and tectonics, working on the morphodynamics of continental surfaces and the links with tectonics and climate. Your previous research was focused on the compressive deformation of continents and associated continental landscapes, as well as the action of rivers on these landscapes. But more recently, you've been concentrated on the morpho-sedimentary processes in deserts, with a particular focus on the action of winds. And this is what you are going to present, I guess, Aeolian landscapes and fluxes from source to sink, and we're very happy to listen to you. So now it's not the scene is yours, it's the screen. The screen is yours now.
Thank you. So thanks, Philippe, for this introduction, and thanks, Isa, for the invitation for this presentation. And yes, so today I'm going to speak about studying Aeolian landscape and fluxes with a source-to-sink perspective, and to try to convince you, if it's not already the case, that this approach is relevant and essential to provide fundamental constraints on Aeolian processes and their contribution to the dynamics of the Earth and other planetary systems. So just a few words. As I joined ISAR Society a few months ago, just a few words to introduce myself and explain where come from the plea I am going to make today for the source-to-sink studies. So as you said, Philippe, I'm a basin geologist, and I was interested for a long time in the multiscale dynamics of continental surfaces. Mostly working on the morphodynamics related to continental deformation and processes in regions such as Central Asia, so several years ago. And during those years, I was exposed to outstanding Aeolian landscape, represented huge volumes of transported sediments. And finally, I could not help but start wondering about these Aeolian landscapes. And so it was naturally that I started working on this topic, trying to implement a source-to-sink approach, which is today a basic approach when you are basin geologist, in fact. So about the motivation for applying this approach to Aeolian system, I will not be too long because they are the same as the ones underlying all the research of the ISA community. So just what we can all, I think, state is that without going into details, that there is still many fundamental questions that remain open about these Aeolian processes, and we therefore need a deeper and more accurate knowledge of those phenomena to improve our current understanding of their multiple effects and interaction with land, atmosphere, ocean, and life. And quantifying the Aeolian landscape dynamics and sediment fluxes, sand and dust, from their sources to their sinks over multiple space and time scale is certainly a strategy that can help us to achieve a breakthrough in this respect. So before to focus on Aeolian system, I propose to remind what is the source-to-sink paradigm and to review some of its general key concepts. And so the source-to-sink paradigm was inspired by some pioneering work carried out before 2000 and before to be formalized some 20 years ago. And it has continuously developed as a major unifying conceptual frameworks of the geosciences since then. In this conceptual framework, the various landscape elements are no longer considered as independent compartments, but as a component of a same sediment routing system, dynamically linked by mass exchanges from sources in regions where sediment are produced by erosion to sinks in sedimentation where sediments are temporarily or permanently accumulated. So at the core of the source-to-sink paradigm, you have the link between landform, their dynamics, and the related sediment fluxes and budgets. So the benefit of working with this conceptual framework in mind are multiple because it can help to translate geological setting and scenery into fundamental processes, parameters, and signals that can be quantified. It can help to provide cross-constraint on sediment fluxes, landscape dynamics, and their responses to changes in boundary conditions, and to invert morpho-sedimentary signal to retrace these boundary condition changes. And finally, it also helps to be predictive in terms of natural hazard and resources. So the first key concept of the source-to-sink paradigm is therefore the recognition of landscapes as sedimentary routing systems through which matter is conveyed, so from source to sinks, by short-term incremental transport events that add up over the long term to shape polygenic landscape whose different landforms emerge and evolve over a range of lengths and time scale, so from centimeters to thousands of kilometers and from minutes to millions of years. Along the transport routes, the landform developed according to a proximal distal logic, for example, upstream, downstream for fluvial system, or upwind, downwind for Aeolian one, etc. So this in the resultant transport direction. From a spatio-temporal point of view, this morpho-sedimentary dynamics is controlled first by what we called in basin geology autogenic processes, that operate in a given configuration of boundary conditions of the landscape over historical timescale. It means shorter than tens of millennia. And then over geological timescale, longer than a few millennia, this dynamics is forced by allogenic processes that correspond to changes at the boundaries of the landscape driven by tectonic climates, life, and now also humans. And these processes affect Earth's surface with trends, rhythm, and aberration over time. For example, it can be a vertical movement of the basement of the landscape or variation in terms of sea level and etc. In response to these boundary condition changes, sediment may be mobilized through the sediment routing systems, leading to the propagation of a signal corresponding to a change of either erosion, sedimentation rate, or sediment flux, or landform morphology, or deposit thickness, or any changes in a measurable morpho-sedimentary quantity. And such a signal propagation involves the mobilization of sediments on a whole range of nested lengths and timescale. So from the motion of grains over a few seconds to a few days, up to the transformation of the entire landscape over a few millions to a few tens of millions of years. So the landscape will adapt to the external perturbation through a whole spatio-temporal cascade of processes with a time of response or return to equilibrium regarding the new boundary conditions that depend on the size of the considered system and on the connectivity between its various landforms, which can be seen as the rate at which these landforms are able to exchange matter between them and through the system. Actually, one of the main objectives of the source-to-sink approach is to clarify how these morpho-sedimentary signals form and propagate and are preserved through the routing system. However, this task is not simple due to the multiplicity of and superimposed of forcing, combined with a nonlinear response of the system, which with many transformations of these signals illustrated in the center. And according to the system equilibrium time, with respect to the initial perturbation and contemporary autogenic processes timescale. And to make the even worse, the recording of a signal also depends on the preservation of its marker, morphologies or deposits over time. On the right, you have an example of this preservation issue through the case of an experimental fluvial delta with a map view above and below the elevation of the sedimentation surface as a function of time, reflecting the sediment accumulation in this sink at the black point on the map view. And where the preserved deposit only represent a period in red, which correspond to a highly discontinuous temporary record separated by period of non-deposition or even erosion. It's mean loss of information. So historically, all these source-to-sink concepts were developed for and extensively applied to terrigenous sediments produced by continental alteration and transported from continental catchment area to deep sea floor by rivers and turbidity currents, which are subaqueous sediment avalanches. And then the scope of the source-to-sink approach rapidly extended to sediment particles of all sizes and natures, to all transport agents, wind included, and to all environment, continental, lacustrine, marine, and even extraterrestrial. However, studying Aeolian system from a source-to-sink perspective is not so simple, because even if they can also be considered as routing system evolving under changing boundary conditions, Aeolian transport and landform are specific enough to require an adaptation of some of the general concepts we have just seen, and as well as specific data and methodologies. So I propose now to review some of these specificities of Aeolian systems. And of course, these specificities are well known by the Aeolian research community, and they will certainly seem obvious to you, but the point here is really to reconsider them from a source-to-sink point of view, bearing in mind that each of these specificities constitute a challenge in itself for applying the source-to-sink approach originally conceived for other sedimentary systems. So to begin with, let's have a look at Aeolian routing systems. So they distinguish by a high level of complexity due to the multiple possible sources and sinks. Sources can be erosional Aeolian environments, but also alluvial fans and plains, beaches, or dry water bodies, such as lakes, dry lakes. Sinks can be dunes filled or loess hills and plateaus, but also fluvial system or water bodies, seas, lakes and seas. And what makes the picture even more complex is that these sources, sinks, and the sediment routings between them depend on the size of the particle, with a continental route for sand and atmospheric ones for dust. So here you don't have only one kind of routing system, but two kinds of routing system for the same transport agent. Then studying these routes is also complicated by the fact that unlike fluvial or tubiditic transport, for example, which are localized along physically well-defined routes corresponding to valleys and channels and which flow downslope, Aeolian transport is a diffuse transport along poorly defined routes, controlled to first order by wind regimes rather than the slope, as it is visible on the bottom left picture where dune climb topography. Sorry. So in terms of source-to-sink, the fundamental difference between Aeolian and other sedimentary systems really lie in this dependency of the sediment transport on wind regimes. It has strong implications for how incremental transport events over a threshold velocity accumulate over time to produce a given resulting transport over a considered period. And for example, here I draw three scenarios with wind roses to the left, corresponding to sand flux roses on the right, and drift potential and relative drift potential in pink and black at the bottom. And for the same DP, the RDP can take different lengths and orientation depending on the local wind regimes. So like these wind regimes, sand flux regimes can thus be unidirectional, bidirectional, or multidirectional with a nonlinear distance-time transport relationship, which is completely different from what happens when transport follows a steeper slope. And last but not least, due to this dependency on wind regimes, Aeolian systems will be sensible to any modification into atmospheric circulation, in addition to the other boundary conditions changes of tectonic, climatic, and biologic origin that also affect other sedimentary systems. So even if this issue remains to be fully explored in the case of natural landscapes, Aeolian systems also theoretically respond to these external perturbations through a spatio-temporal cascade of mass exchanges with a characteristic time of response illustrated here for dune landscapes from sun grains to sun seas proportional to the system size, which can be expressed as an area in 2D or a volume in 3D, and proportional also to the sediment flux. So to document Aeolian routing system, their route, discharges, or characteristic time, it is thus critical to estimate wind-blown sun and dust fluxes despite of their diffuse nature. And to date, the analysis and quantification of these fluxes rely essentially on two approaches with their strength and weakness. On one hand, a physical approach based on transport laws, which integrate various parameters of wind regime and soil properties, characterized by a high natural spatio-temporal variability, which is difficult to constrain. And in the other one, we can also use a geomorphological approach based on the morpho-sedimentary dynamics of erosional and depositional Aeolian landforms and landscapes, such as yardungs, dunes, dune fields, loess hill, and etc., of various sizes and characteristic times of evolution, and which naturally integrate the spatio-temporal variability, but which are inefficient to bring constraint on the short-term properties of transport events and their control through time. So consequently, integrating transport laws into desert landscape dynamics to perform a complete and accurate mass balance for windblown sediments, including continental and atmospheric fluxes at the scale of a whole desert, still remain challenging. So the other major source-to-sink objective that need to be fully achieved for Aeolian system is the comprehensive characterization of the morpho-sedimentary signal that may form and propagate and preserve under changing boundary conditions as in other environments. These signals have been already recognized for decades as depositional sequences in sedimentary basins, as shown on the right. But they are just at the beginning to be convincingly detected in the morphology of Aeolian landforms. And regarding these signals in terms of sediment flux, they are well documented for dust, even if their link with desert dynamic is not yet not always clear. And while for sand, everything remains to be done in terms of signal of sediment flux. So to sum up, due to the specificity of Aeolian systems, many challenges must be faced to characterize and understand their source-to-sink sediment fluxes, morpho-sedimentary dynamics, and sedimentary records. But in fact, today we have many opportunities that can help us to tackle these challenges, such as the development of the source-to-sink paradigm, for example, the development of our knowledge of Aeolian transport and dune morphodynamics, of wind data, both measurement or numerical model outputs, with space and time resolution of up to 1 hour and 0.1 degrees, even in deserts. And also we have a development of observational methods and data for continental landscapes and sedimentary series. And also we have more and more relevant experimental and numerical modeling. So today it's a very we are very lucky, in fact, to benefit from a whole conceptual and methodological toolbox, in addition to extensive databases to deepen the source-to-sink analysis of Aeolian processes. So let's now have a look at some Aeolian source-to-sink studies and their contribution to our knowledge, or how they can contribute to the knowledge of Aeolian system. Of course, this is a selection, and it is far from being exhaustive, and there are many valuable studies that I won't go into here, but I will try to illustrate a range of relevant strategies from the oldest or more widely recognized and routinely implemented to the more recent and novel one. To begin, I would like to pay tribute to two pioneering and visionary work well before the advent of the source-to-sink paradigm to the top. Indeed, by describing the sand flows across Sahara from wind measurement and discussing the sediment budget of the associated sand seas from satellite imagery, Wilson, Manguet, and Chemin were the first to introduce source-to-sink consideration into the analysis of Aeolian systems in the early 70s and 80s. And since this pioneering work, most of the Aeolian source-to-sink study belong to one of these three categories. The first one, illustrated to the bottom left, is the provenance based on the geochemical, mineralogical, and geochronological feature of the sand and dust particles. Then in the middle, you have the dust storm tracking based on remote sensing dust proxy, usually combined with wind measurement and numerical data. And to the left, I illustrate Aeolian sequence stratigraphy based on sediment outcrops and cores, and which aim to clarify the mechanism by which Aeolian landform deposits and their forcing are translated into the sedimentary record into sedimentary basin. However, one word about this stratigraphical model, which were mainly developed to explain ancient Mesozoic sedimentary records, and which did not account for certain observations that can be made in the case of more recent Cenozoic sedimentary series overlaid by a still active sand sea. So either the Cenozoic boundary condition of Aeolian sinks have something different compared to more ancient time, or we are still missing something fundamental about Aeolian deposit preservation. Lastly, one can also mention work dedicated to the description and measurement of Aeolian erosion, sedimentation, and sediment fluxes, but these studies are generally limited to a single component of the sediment routing system and budget, such as erosion or accumulation, or sand or dust, and without a real source-to-sink integration. So to address this issue, the aim of the recent PhD work of Colin Chanteloube, co-supervised by Clément Nartois and myself, was to combine the approach of Wilson, Manguet, and Chemin with the current wind data from the RERA sampling climate reanalysis, digital topographies, and chronostratigraphical methods to develop a multi-scale source-to-sink strategy of analysis of Aeolian landscapes and fluxes. As a first case study of this strategy, we selected the Lut Desert in Iran for two main reasons. First, this desert is renowned for its outstanding Aeolian landform, which are organized in a mosaic of erosional and depositional features corresponding to neighboring sources and sinks belonging probably to the same Aeolian routing system. And second, this desert has also the interesting particularity to be nested in an endorheic watershed. So you can see to the left, well, I don't know if we can really well seen, but there is a green line which correspond to the water divide on the satellite image. So the water divide surrounding the Lut, within which a sediment budget can be assessed without mass loss due to river transport. So the first step of this study was to identify and locate the various Aeolian landscapes through a morpho-sedimentary mapping. This mapping reveals that erosional landform concentrated in the western part of the desert. They correspond to huge depression outlined in red, and which contain mega Yardan fields outlined in orange. And the formation of all these erosional landforms can be dated thanks to chronostratigraphic markers such as pre-incision lava flows mapped in black and dated around 2.35 million years, and a set of sea incision terraces of the huge depression, the youngest of these terraces being dated around 110 kilo year. So in contrast to depositional landform, in contrast to erosional landforms, the depositional landforms are located in the eastern part of the desert, and they correspond to isolated dune fields and around a vast sand sea outlined in blue. Once mapped the erosional and depositional Aeolian landform in the Lut, we described the short-term sediment transport over the last decades by calculating the modern transport properties based on the surface wind data from the Era-Sankland climate reanalysis. Injecting this data into transport laws validated from dune dynamics, we computed wind roses, flux roses, and a set of parameters such as the drift potential, resultant drift potential, resultant drift direction, and so on, across the whole area. This transport property discloses the modern wind regime and sound flow in the Lut. On the map to the left, you can see those fluxes in green, which display an unimodal transport to the west, becoming bimodal to the south and east, and multimodal in the center of the desert. And the derived sand flows plotted to the right thus organized into a cyclonic transport pattern converging toward the Lut center. Integrated over time, downwind of the Medagar-Yardan field and upwind of the Sand Sea, this sand flow provides a short-term erosion and sedimentation rate, as well as output and input sediment discharge over the last 40 years. To assess the medium-term sediment transport over the last millennia, we then unraveled the wind regimes and transport properties over the timescale of dune growth and migration from the bedform orientation predicted from the wind data and observed on satellite image. These dunes display different patterns from erosional sources to depositional sinks, with trend of small backends conveying sand between the Medagar-Yardan to the west, longitudinal dune transferring sand from the Yardan's field to the Sand Sea to the south, and the giant transverse bedform in the Sand Sea to the east, with finally giant star dune in the center of the desert. Sorry, there is some noise. I hope it's not. It's still okay for you. So by focusing on the sound fluxes and characteristic times associated with those giant dunes, we estimate medium-term sediment discharges over the last 6 millennia. So eventually, to document the long-term sediment transport over the last million years, we retrace the paleotopographic evolution of the Lut Desert based on the remote sensing data, satellite image and digital elevation model, and chronostratigraphic constraints, such as the edges of the lava flows and terrace presented before. From the elevation differential between the successive paleotopographies, we reconstruct volumes eroded from the depressions upwind in red and deposited in the dune field downwind in blue, with sinks remarkably located upslope of the source in this desert. And this volumetric reconstruction and their time constraint give long-term erosion and sedimentation rate, as well as sediment discharge over the last 2 million years. So thanks to this interdisciplinary and multi-scale source-to-sink analysis strategy, we quantified the contribution of Aeolian processes to sediment transport and landscape evolution in the Lut Desert. In this desert, we show that the modern wind regime combined to create an internal routing system for the sand which is consistent with the spatial organization of the erosional and depositional quaternary landform. And moreover, in this routing system, the Aeolian erosion and accumulation rates are on the same order of magnitude of 0.1 millimeter per year, while the source to sink discharges have the same order of magnitude 2 within the uncertainties, around 1 million of cubic meter per year from decades to millions of years. So consequently, in that case, modern sand flows are sufficient to explain the exchange of mass between quaternary landforms, which suggests a persistence of wind regimes and transport properties in the area over historical to geological timescales. Thanks to the endorheic setting of the LUT, we were also able to perform a sediment budget for the wind-blown sediment, including sand transport and dust emission at the scale of a whole desert. And this budget is unbalanced between the matter excavated from the erosional depression and the sand accumulated in the dune field, which demonstrates that the LUT is not only a sand trap, but also a major source of dust that could account for as much as 85% of the mass transported by the wind in the area. And just for comparison, here is a plot of fluvial sediment discharges over historical against geological timescale, with a range of the LUT values for Aeolian processes represented by the red square, and values which are of the same order of magnitude than river catchment areas around 10,000 square kilometers, which is not negligible, obviously. Based on the same kind of satellite imagery and digital topography used in our study in the LUT, it is also possible to work on sand routing system on other planets. To illustrate this, here is an example of, for example, an example of two studies on Mars by Ruben and Co, Gwen and co-authors, and which documents the global Aeolian sand routing system from Barkhan's migration to the right and sand sink location, volume, and accumulation rate to the left. So yeah, it's work also outside of the Earth, this approach. Always from the same type of data, it is also possible to go further in our quantitative description of the nature, propagation, and preservation of morpho-sedimentary signals. For example, this recent study by Andrew Gunn to the left that recently explored the time taken to form and reorganize dune fields. Based on wind and topographical data, it shows that in the Rub' Khali Desert, these characteristic timescales are outpassed by climate changes, and discuss the implication for stratigraphic interpretation. Using other dune features, Marvin and co-authors to the left demonstrate that morphological metrics, in their case, the density of dune interaction, which can be characterized by the spacing of the crestline, within a dune field can be also used to detect and possibly quantify recent changes in boundary conditions, such as a shift in wind regime or varying sediment availability. They also shown that the dune field with the longest bedform characteristic time are those where the persistence of this signal is the longest. So all the inputs of these studies really fall into the scope of the source to sink objective, of course. Finally, source to sink studies on the atmospheric component of Aeolian systems we don't have to forget those kind of studies also. And I'll demonstrate this by this couple of articles by Skronieski and co-author, who are focused on tracing dust transport events in Western Africa from the Sahara to the Atlantic Ocean over days to hundreds of thousand years. And in these works, they first computed three-dimensional air masses back trajectories of dust storm, handicapped at a meteorological station where dust was also collected and it's pronounced geochemically characterized, as you can see to the left. And the different geochemical signatures were then found in the current sediment of a marine core located downwind of these storms in the center, thus opening doors to an interpretation of the spatio-temporal dynamics of these storms over the last 210,000 years from the dust content of the quaternary sediment of the same core, shown on the right. So finally, before to conclude this presentation, I would like to share with you some current work by young researchers, works which are, in my opinion, very promising regarding the source-to-sink analysis and understanding of Aeolian systems. The first of these studies is the PhD work of Jimmy Denack, which opens up a new perspective for studying source-to-sink organization and dynamics of dune landscapes. At desert scale, but with a bed form resolution. So using EA, Denack and co-authors have developed a new workflow to perform extensive dune mapping and morphometric measurement from topographic data. Here you have an example for the Rub al-Khali in Saudi Arabia, where more than 100,000 bedforms have been mapped, and their width, height, elongation, and etc. Other metrics have been measured over hundreds of thousands of square kilometers. Thanks to her statistical analysis, it is now possible to highlight and discuss the continuum observed between the various dune patterns, the spatial distribution, or other features of the Sun Sea according to its boundary condition, starting with wind regimes, of course. The second study I would like to highlight offer perspective in terms of sound flux quantification at desert scale. It is a work by Najibullah Sadid, who mapped and measured dune migration over a few years in the Dasht Imago Desert in Afghanistan, before to convert this migration into sound discharge. As you can see here, using a remote sensing approach from satellite imagery and topographic data. So based on this study and the multiplication of such data, one can imagine that in the near future, it will become possible to monitor sound discharges across the dune field and Sun Sea over several months to years, depending on the size of the documented bed form. Beyond quantifying the sound flux alone, the goal of Jean Verité's postdoctoral works is to bridge the gap between sound transport, dune morphodynamics, and dust emission, using the numerical model we scale to the middle left. Jean and co-authors propose an empirical laws for sound flux over dunes and in interdunes according to the incident angle of the wind and aspect ratio of dunes according to this angle. This empirical law indicates that the greater the angle between the wind direction and the dune crest, and the greater the sun blasting of the interdunes. So this prediction is now being verified on linear dune fields developed under a bidirectional wind regime in the Tibesti region from an analysis of dust emission based on a Sentinel-5 aerosol index. The first stage of this analysis suggests that preferential zone of dust emission in light colors to the top right are related to dune fields, and that for equivalent transport event on flatbed, we do seem to observe a dependency between the dust emission and the wind incident angle, as you can see to the bottom left. Finally, I don't want to forget the thing, because I'm basin geologist after all. And we still need to refine our understanding of the preservation of Aeolian deposits in sediment sinks. And the joint thesis work of Victor M. Delacote and Chester Davis, which combine field observation with numerical stratigraphic modeling, could be a productive strategy as it has been for classical source-to-sink systems. And stratigraphic modeling, for example, sorry, for Aeolian research, still, yes, need to be applied widely. On the left, you can see, for example, a measured description of the stratigraphic architecture of Jurassic Aeolian deposits popping out in Arizona, based on sedimentological logs and 3D photogrammetric models. And on the right, you have the corresponding numerical models whose boundary conditions have been adjusted to reproduce the main characteristic of this architecture. Based on the comparison of the observed and modeled geometries, Chester, Victor, and their co-authors can then discuss the respective influence of external factors such as the water table level or sound flux, and internal factor, the dune dynamics, in the construction of the studied sedimentary records. On this slide, I reproduce finally the historical step of development identified in a recent synthesis about the traditional source-to-sink approach applied to fluvial to turbidity system with the birth of the second stratigraphy, which provide a logical and deterministic framework for the spatio-temporal organization of the sedimentary record in sinks related to their boundary condition. The development of a variety of data and methods to quantify sediment fluxes, then the achievement of sediment budget, then the leap in scale to our systematic approach, and finally, the look for better understanding and inversion of the morpho-sedimentary signal. Comparing the state of maturity of the source-to-sink studies of Aeolian system to this traditional approach, it appears that probably because of the specificity of the Aeolian systems and related challenges involved in their source-to-sink study, the source-to-sink Aeolian research is still in its infancy. So accordingly, the potential of this approach remains to be fully explored and exploited to bring original and quantitative constraints on Aeolian processes and their coupling with atmosphere, hydrosphere, and biosphere also. And this is something I find very exciting. So to conclude this presentation, I hope that you are convinced by the benefit of deploying this source-to-sink approach on Aeolian systems. And my take-home message being that as other sedimentary systems, Aeolian landscape can be seen as sediment routing system, which conveys sediments from erosional sources to depositional sinks, according to their internal dynamics under changing boundary conditions. But studying this Aeolian system is specific and challenges with numerous current and exciting opportunities and perspective today, and needs for integrated and interdisciplinary studies from sources to sink, from grain to desert land and timescale, from continental and surfaces to seafloors, and from present to this past. So if we can do that in the coming years, there is no doubt that we will be able to bring original constraint on the organization and dynamics of dry land of the Earth, and also, as you have seen, of other planetary bodies such as Mars or Titan. So thank you for your attention. And yeah, I wait for your questions.
Wow, many thanks, Laurie, for an excellent presentation, taking us really all the way from milliscales to macro scales in both time and space. Thanks a lot. And also for, I think the last few slides, we were presenting some new speakers for our virtual seminars, more interesting subjects. Many thanks. I'm sure there are questions, and please feel free to put them in the chat, or use the Zoom function to raise your hand if you want to ask the question yourself. And to start off the discussion, maybe I can be so bold to ask my question about the LUT system, which I'm found really intriguing study, amazing work. But I was wondering that you see dust plumes coming off the of the sands, right? So parts of them are redeposited and going in a loop and going back north, but some material must escape southward because you see them in the plumes. Do you see that back in the particle size distribution of the material? Does it get coarser grained, let's say?
Alors, excuse me, I try. In fact, can you still see my presentation?
Yeah, we see the
because
last slide with
I
the
cannot
next.
see it anymore.
Okay, we are seeing the last slide.
I try to reduce the.
Maybe you can unshare and share again your presentation, or
Don't know, because I would like to come back to the root slide. Okay, I will try to come back. Yeah, I think it's okay. So in fact, what is mapped on the left maps is really the sun flows. So it's really for particular size around 180 micrometers. And this is calculated, those trajectories only considering the wind 10 meters above the ground. So it's really trajectories for sun flows. And in fact, we don't in these studies we don't really look at the dust plume. And in fact, it was a surprise when we try to balance the volume between the erosional depression, the erosional sources, and the dune field sink. So dune field, we have considered, in fact, something I have to say, we could not go in the field. So we at some point we had the hope to get some field constraint, but about the grain size and the transported grain size and so on, but we couldn't go there. And so we just use a 180 micrometers size for the sand, and we didn't really know in the erosional source our proportion of sand we have in the sedimentary series that have been eroded, and the proportion of fine grains. But when we consider that in the dune field, we only had the sand. And when we try to balance the two volumes, in fact, we see that we have a lack of a huge amount of matter. So that's why we propose that since the loot is in a water in a closed watershed, so we propose that the only way to lost matter in this setting is to make a dust emission. So what should be interested it's to use now some an approach such the one Jean Vérité is developing during his postdoc, to have a look to this dust plume and how they are related to sun blasting on the ground. But for the moment, we didn't do these studies. And the only thing I can say is, I don't know, it's a little bit small. I don't know if you see, there is a small satellite image to the top right, and this satellite image I chose it because there is a dust plume going south out of the basin.
Yep,
So
that what kept me intrigued to see that indeed some material must escape.
yeah.
Yeah.
But there is many studies done on dust in this area, but they mainly focus just to the east, because to the east you have the Sistan basin, and which is a really hot spot for dust. And many of the studies about dust in this area focus just a little bit more to the west. But it would be interesting to look at, yes, the dust emission, and see if we can yes, cross constraint with the sound flow we can describe.
Yeah, very nice. Thanks a lot. There's more questions in the chat now.
Yeah, we have a question from we have two questions, one from Philippe and one from Minxing. I might ask Minxing's on her behalf, because Philippe and Laurie have plenty of time to discuss this if we run out of time. She asks, how do you determine the line of the paleo surface of pre-erosion / deposition? I
Yeah.
assume this is the this is for the Yardangs in the
Yes.
Lut. Yeah.
Okay. So, in fact, I don't know. I don't have an additional slide, but maybe we can have a look about this one. Oh, yes.
And bear in mind we're
yes. In fact, so the Lut Desert is into an endorheic watershed with a mountain range all around, and in fact, in the middle of this mountain range, all the river fluxes of these mountain sediment fluxes of those mountain range converge to the center of the Lut Desert, and which is, geologically speaking, which is a sedimentary basin, basically. And in fact, this sedimentary basin was filled up to a certain point by the sediments delivered by rivers. And in fact, around the colored shape that represent, in fact, isopac maps. It means maps of volume, sedimentary volume, a lacking sedimentary volume in red. That we reconstruct by, in fact, by using the top of the sedimentary pile into the basin that is not, again, is not eroded yet. And in fact, so we have the top of this sedimentary pile all around this depression, and even into the depression, there are some topographical remain of this previous surface, which correspond to the top of a sedimentary series. And at some point, and this is something very interesting, because it should be, yes, understand at some point. In fact, the mass balance change, and the wind become. Well, I don't know if the mass balance of the basin changes at the before 2.35 million years. The mass balance of the basin was positive, and the river brought enough sediment to fill the basin. And at some point, the river fluxes become not enough to compensate the Aeolian fluxes, and you start an erosion. But you have a remain a topographical remain of the top of the sedimentary series. So when you interpolate the topography where now you have some erosion, you can reconstruct the yes the lacking sedimentary series. I don't know if I'm clear.
I think it makes sense.
Yeah.
It's a little confusing because at least on my screen, your cursor is often like to the left of where I think you're pointing on your own screen. But it's okay. You were pointing at, I think, I'm not sure if it's the same for everyone, but I think we should probably end it there because we're past the hour. Is that okay for everyone? Philippe?
Yes, sure. I think we had a full hour of the. That was a very nice presentation. Thank you, Laurie.
You're welcome. Thanks for invitation.
A lot of information, and I have also many questions. But as Andrew said, we can just meet in the room next door, so that's easy. Thank you, everyone, for attending this seminar. Don't forget to register for the next ones. We've seen we have a very nice program until the end of July. The next one is in March, the 14th of March, by Tom Gill, who got the Career Award of ISAR. Yes, that's it. And so keep you posted with the ISAR information. If you don't receive emails, go to the website of ISAR and get connected, get an account so that you can receive the newsletters and all various announcements. Maybe JB, Andrew, you have something to add, but I think that's it, right?
Yeah, I think I thank you very much, Laurie. That was an excellent talk. Really exciting, and yeah, lots of really interesting information. But that was the thing, Philippe, I guess, is that we've switched systems. Is that right? And so if you want to continue getting the newsletter and updates from ISAR, you need to re-register on the website with your email address. That's a big thing for everyone to do. If I'm getting, if I'm understanding correctly.
Yeah, that's correct. That's correct. Yeah.
Okay, good. Yeah, cool. Okay.
Yeah, so the website just dropped off this slide, I'm afraid, but the address is aeolianresearch.com, so it's not hard to think. All right. Many thanks, Laurie. It was really nice talk. Learned a lot, and hope to see you for the next talk in 14th of March.
Bye-bye.
Thanks,
Bye-bye.
everybody.
Thank you. Bye-bye.
Have a good night or good day.
Yeah.
Bye.